Hello and welcome to the chapter on acids and bases. So what this chapter is it's the last chapter. It's the same thing. It's the equilibrium constant with slightly different letters. What we're going to be doing is a bunch of equilibrium problems, a bunch of equilibrium problems in different ways. And we're going to use some different letters, but it's all equilibrium problems. So if you got a good grasp on the equilibrium stuff, this stuff isn't that much harder. There's a lot of it. It's very long, intense material, but it's just a bunch of equilibrium problems. The trick is going to be figuring out which kind of equilibrium problem am I doing so that you can do it successfully. So just an overview of this chapter, we're going to be talking about the quantitative part of acids and bases, but with pH, using Ka, the auto-ionization constant, or the ionization constant to calculate acid strength, and we're going to compare those kind of things. We're also going to talk about qualitative things. What is the ionization constant? What are conjugate acids, conjugate bases? How is acid strength related to molecular structure? We're going to talk a lot about buffers. Buffers are incredibly important, especially for biological systems, but also in a lot of chemical systems, which is a way to maintain pH. And we're going to talk about how we do that, how their capacity is, how much can they maintain pH when they're faced with acid and bases. And then titration. You've seen titration before in previous chemistry classes, but we're going to go into titration in excruciating detail. We're going to be able to calculate any point on a titration curve like that. Well, maybe not like that. Maybe like... Okay, so, there's a little bit of work involved. But that's what we're going to be doing in this chapter. So, what is an acid? There's three major definitions for an acid. One of them is by far the most common, but we're going to talk about them. Some textbooks, and you'll see things, we'll also talk about conjugates here. I talk about that in a different place because I like it better there. So, we're going to talk about the three major definitions. One is the, I'm sorry, I don't know why I put that H first, the Arrhenius definition. Hey, and you're like, hey, we've seen Arrhenius before. Yeah, it was amazing. Back in the days when a lot of the stuff was first being discovered, one scientist could discover things in like 50 different fields because there was so much ripe for the discovering. It's a little harder nowadays. So people like Arrhenius and stuff, their names all over all sorts of things. But the Arrhenius definition is very simple. An acid gives off H plus in solution, and a base gives off OH minus in solution. Very, very simple definition. So acids, you're all familiar with hydrochloric acid. HCl goes to H plus plus Cl minus, and these are all aqueous, right, dissolved in water. All of our acid-base chemistry we're going to talk about in water. We're not going to talk about acid-based chemistry anywhere else. So all of this is going to be aqueous. So aqueous HCl falls upon H plus and Cl minus. Therefore, it is the Arrhenius definition of an acid forming H plus in solution. And then what do we have also? We have things like our favorite sodium hydroxide aqueous falls apart into Na plus and OH minus aqueous. And again, that is producing OH minus in solution, and so that is an Arrhenius definition of a base. But it turns out that definition is very, very limited because there's also chemicals out there that don't have OH in them, but yet are basic. So they can't produce OH directly, but they can act as bases. And so a couple of other folks named Bronsted and Lowry, not related to the seasoning salt that you put on everything, and it's really good seasoning salt. Take some chicken, put some seasoning salt on it, put it in the oven. It's great stuff. Anyway, Bronsted and Lowry, and some people will put that little accent there on that. I don't know what the name of that accent is. I took French. I didn't take other languages, and they don't have that accent in French. What this definition does is it allows for a kind of wider range. So acids are very, very similar, but we say this. We say they are a proton donor. You're like, protons? Where'd you come up with protons? Remember, what is H plus? Hydrogen has one electron and one proton. And if you take away that electron, what's left? A proton. And so when we say proton donor, we are also saying H plus donor. So it's a little bit different. It's not saying it's giving off H+, but it's giving H+. So slightly different, and we'll see what that means. Bases, no longer defined by OH-, but actually defined by the protons, and they are proton acceptors, or an H+ acceptor. So let's look at an example. We're going to look at ammonia, NH3. Now NH3 aqueous, when you add it to water, what happens is the NH3 actually takes a proton from water to form NH4+, and also OH-. So you can see that even though NH3 has no oxygen in it, it can't produce OH- directly. The balanced reaction here allows it to produce OH because it took an H away from water. That H went over to the ammonium ion, NH4+. And so we now have NH4+ is the ammonium ion hydroxide, and we can see it's acting as a base. Also in the previous definition, right, because it was producing OH, but it's a little technically off because it had no OH to produce with. So here we can just watch what happens to the proton. The proton left the water, leapt onto NH3. That makes this water, what? A proton donor, or an acid, and it makes the NH3 the proton acceptor, or the base. And so the Bronsted-Lowry definition is by far the most commonly used definition. When you're thinking about acids and bases, you're going to think mostly about that proton. Where is that proton going? You'll notice I did use the double reaction arrows there, indicating this is an equilibrium. So ammonium and ammonia simultaneously exist in solution. But it turns out that some people said, oh, hey, that's not good enough. Let's try to make this definition even more flexible. And you get what's called the Lewis definition. And you may remember Lewis from Lewis structures, right? All those electrons. So guess what Lewis does in his definition? He talks about electrons. And he says this: an acid is an electron pair acceptor, and a base is an electron pair donor. Applies to everything. It applies to all these different ones. But how can it? How can we talk about an electron pair acceptor and electron pair donor when we're talking about ammonia and water and watching this proton move around? Well, let's look very simply at water. In the previous case, the water reacted with the ammonia. We ended up forming OH-, and let's look at those electrons. If we were to draw the Lewis structures for them, we have this, that OH used to have two H's. Then this guy left, right? But he left as an H+. So what did he leave behind? He left behind this pair of shared electrons right there on the OH. So when the H+ left, he left that pair of electrons behind, which means that water accepted the electron pair. Okay, so that makes it the electron pair acceptor. An electron pair donor, that would be the ammonia, because if we draw the Lewis structure of ammonia, NH3, it's got that lone pair on it. And that H+ that we got from the water comes in there and says, hey, I would like your electrons, because, you know, I want some electrons. And ammonia says, sure, you can have my electrons. Let's share them. And then they form the NH4+, which looks like this. So we have ammonia donating that electron pair to the hydrogen ion. That makes it an electron pair donor or a base. And we have the water taking that pair of electrons when the hydrogen leaves, becoming OH-. I should put the minus around here. Becoming OH-. And so it is the electron pair acceptor. So we can use it for all the normal acid-base definitions. We can also use it for kind of more specialized cases that don't look like acid-base chemistry. AlCl3 plus NH3 can form Cl3Al and NH3. So those two can bond together. What's happening? Well, if you remember from your Lewis structures, AlCl3, the aluminum actually only has 6 valence electrons in it. The ammonia, what we just drew earlier, has that lone pair. And the ammonia donates its lone pair to make a bond between nitrogen and aluminum. So you have nitrogen there donating that lone pair. If it is electron pair donor, that makes it the base. And aluminum accepting that electron pair, which makes it the acid. So we can actually use it in cases where there's no hydrogens transferring at all. There's just some sort of bonding related to lone pairs. So it's the most flexible definition, but it's also the most confusing. It's not as intuitive as the other definitions. So like I said, most people will just use the Bronsted-Lowry definition as their basic definition of an acid. No pun intended, but it was a good pun, wasn't it? Rewind if you need to. Okay. Moving on, common acids and bases, things you've seen around. Hydrochloric acid, right? We've seen that all sorts of chemistry, HCl. It's used for lots of things. It's in our stomach, right? The primary component of your stomach acids is hydrochloric acid. Sulfuric acid, great chemical used for tons and tons of things. Lots of fertilizers, manufacturing, production, batteries, electroplating. Nitric acid, nitric acid, also fertilizer. So you can see there's a lot of very common acids that we see all the time. You'll notice in pink there in front of each one of them, you have that leading hydrogen. And that leading hydrogen is almost always, unfortunately not always, because this is chemistry and there's always exceptions in chemistry, right? But that leading H is almost always an indicator that you have an acid. So if someone writes, hey, I've got H, blah, 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 probably they're telling you I have an acid. Okay? They're not trying to tell you I have something else. There's exceptions. I'm not in control of the world. Okay, it would be great if there were no exceptions. But that's an indicator, so look for that. Whereas if you see an OH at the end of a molecule, oftentimes, but again, a lot more exceptions, we're talking about a base. So an OH at the end of a molecule often indicates a base, but it doesn't always. We'll see other indications of bases as well. All right, so let's look at some common bases that we have. Sodium hydroxide used in all sorts of things. Soap manufacturing, so if you like to use soap, and I really hope you like to use soap, manufactured using sodium hydroxide. There's no sodium hydroxide at the end if you make your soap properly, so you don't have to worry that you're rubbing caustic stuff all over yourself. Sodium bicarbonate, so baking soda. Baking soda is actually a base. And ammonia, used very often. You can get ammonia-based glass cleaners. That's what that smell stuff is when you go and spray your glass. That's what you're smelling. Okay. So we've got some acids. We've got some bases. We know what they are. Okay? So now let's do something with them. What we're going to do is we're going to talk about a generic acid. Why? Because it just makes it that we can talk about anything else we want to later. So our generic acid, it's really a funny name. We call it H, right? H in front of A. A is a generic thing, so it's our generic acid. HA is our generic acid. And what we're going to do is we're going to put that acid into water, and we're going to have it fall apart into H plus and A minus aqueous. Now, since this is an equilibrium, I drew those double arrows there. This is a K, right? This is an equilibrium expression. We can write our equilibrium expression KEQ is equal to, we know how to do this, concentration of H plus, concentration of A minus over the concentration of HA. And there's nothing special about that. You guys know how to do ice tables now. You could have some initial things. Oh, I start with 0.35 molar HA, and you could figure out our concentrations of H plus and A minus and HA at equilibrium. You know how to do that. But here's what we're going to do. We're going to say, hey, this is a special case. This is a special case because acids are so common. We're going to give it its own name. And instead of KEQ, we're going to call it KA. And that's it, folks. That's the only difference between KA and KEQ is the A. It's the exact same expression. There's no difference. So why do we have this separate name for it? Is it just so that we can have all these letters to confuse you? No, it's actually to guide you. When you see a Ka, you know that you're talking about a reaction where HA falls apart into H plus and A minus. So you immediately know the equilibrium reaction you're talking about without someone having to tell you that. And that's why these sub-expressions of K are going to be really, really useful, because if you're aware of them, if you're familiar with them, I can just say, oh, I've got a Ka, and boom, in your brain, you're like, okay, that's an HA falling apart into H plus and A minus. I don't have to actually tell you that that's my equilibrium expression anymore. So these are intimately associated, and you should know one from the other. When you see HA fall apart into H plus and A minus, you should think Ka. When you think Ka, you should think HA is falling apart into H plus and A minus. We're going to do it so many times that you'll be used to it by the time you're done just practicing it, okay? So nothing exciting. It's nothing new. It's things you've all done before, okay? Now, if we really want to be fancy, we can write HA reacting with water to form H3O plus. We've talked about hydronium ion. It was all the rage when I was taking chemistry, but it's kind of fallen out of favor a little bit now just because it's harder to write than H plus. But you know, it's a more accurate representation. If you've got a positive proton in there, it's not going to be all by itself. It's going to be surrounded by water molecules. So that's why people use the hydronium. And this K is going to look a little slightly bit different, right? It's going to look like H3O plus times A minus over HA. Remember, water is a liquid, so we don't put it into our K expression. But if you remember, H plus and H3O plus are the same thing. So these two K expressions are actually exactly the same. There's no difference between them whatsoever. They are both Ka. Primarily, I'm going to use this top version just because I am a little lazy. I don't want to write H3O plus every time. I don't want to have to write that water balancing it in there. But that's actually a better idea of what's actually happening, right? The HA is donating its H, not just to space, but to actual water molecules. All right. So those are our acid dissociation constants. Ka. Nothing different. Ice table. Boom. We'll see that in just a little while. All right. But a couple things we need to know about acids is not all acids are equilibrium acids. Some are what we call strong acids. Okay, what is a strong acid? Well, a strong anything is something that does its job well, right? A strong cleaner will get off all sorts of grease. A strong person will be able to lift all sorts of things. A strong acid is like the epitome of an acid. Well, what is an acid? An acid is a proton donor. So a strong acid is going to be an epitome of that, and it's going to donate protons really well. So something like HCl, aqueous, when you put it into water, and again, I'm using the shorthand notation. I'm not writing that plus H2O to get the hydronium ion. Gives me my H plus Cl minus. And you can see that HA form, right? The A here is Cl, right? HA goes to H plus Cl minus. That is a really, really strong thing. So we don't use these equilibrium arrows to say it. We use just the right arrow that says this happens completely. And that's what a strong acid is 100% dissociation. So you put HCl into water, what you get is H plus and Cl minus. There is no such thing as HCl in water anymore. It just doesn't exist. Now, those of you who know a little more chemistry, yes, there's a few molecules. Okay, we're not going to pay attention to those. Such a tiny fraction, not worth worrying about in our world. Okay, so 100% dissociation falls apart completely into H plus and Cl minus, and that is the definition of a strong acid. Now, why is that important? Well, because if you have a strong acid that's not in equilibrium, you need to know that. Because what we're going to be doing a lot is finding acid concentration, H plus concentration. And it's going to be different if it's a strong acid versus a weak acid. Because a strong acid is, hey, if I put a mole of HCl, I'm going to get a mole of H plus. If volume's not changing, 1 mole divided by 1 liter perhaps, I put 1 molar HCl in, I'm going to get 1 molar H plus. So that's really important because what we're going to find with the weak acids, which we'll talk about in just a moment, is when we put in 1 molar of the weak acid, we might only get 10 to the minus 5th molar H plus. So not much dissociation. So we need to know our strong acids. How do we know our strong acids? There is a list of them. It is HCl, HBr, and HI. So you see our 3 halogens there: hydrochloric acid, hydrobromic acid, hydroiodic acid. What's not on that list? HF. Why? Because fluorine is the weird person. Like, he's just not normal compared to the rest of everything. He's so tiny and does so many weird things that we actually don't put him on that list because he actually turns out to not be a strong acid. I mean, that's why he's not on the list, because he's not a strong acid. But fluorine's always the exception to everything, isn't he? I mean, he's just this crazy little atom. Anyway, so HCl, HBr, HI, those are 3 of them in a row, right? ClBrI, you can see them down there on the halogens. The other ones, HNO3. Be aware, not HNO2, HNO3. Nitric acid, not nitrous acid. 2SO4, sulfuric acid. When it falls apart, it's going to fall apart into essentially completely and form those H pluses. And the last one is HClO4, perchloric acid. You will see some lists if you look on the internet and looking at other places that will include phosphoric acid here. I don't, just because your textbook doesn't. Okay, so phosphoric acid, we're going to treat it as a weak acid. It's kind of on the edge, right? Is it complete dissociation or not quite complete? And it's not quite complete. So your textbook does not include it on the list of strong acids. So 6 strong acids, you need to know these. Right? You need to know those because you need to be able to recognize right away, do I have a strong acid? Do I have a weak acid? Well, how do you know if you have a weak acid? Because it's not one of those. There's only 6 strong acids. Everything else is a weak acid. So if you run across an acid you've never seen before in your whole life, you're like, I don't know, is this a strong acid? Is it a weak acid? I don't know. It's a weak acid because it's not one of these 6 strong acids. That's all you need to know. Okay? So recognize those 6 strong acids. Everything else is a weak acid. Right? What is a weak acid? It's something that does not completely and 100% dissociate. So if we take our other good friend that we just talked about, HF, and we write its equilibrium reaction now it looks a lot more like our HA expression, right? HF, and F minus aqueous. What happens when we put this into solution? When we put this into solution, mostly nothing happens. It's just HF. There's aqueous HF. It's surrounded by water. It's definitely aqueous. It's not like separated from the water, but there's not very much H plus and F minus in there. There's some. Right? And how much is determined by our equilibrium constant, an ice table, all that kind of stuff, which we'll get to in a little while. So we do know how to do this kind of stuff. We do know how to deal with a weak acid and trying to figure out H plus concentration. But the strong acids, you got to recognize them. So you can say, oh, look, 0.1 molar HCl gives me 0.1 molar H plus. 0.5 molar HBr gives me 0.5 molar H plus. Whereas 0.5 molar HF does not give me 0.5 molar H plus. I've got to do my ice table and figure that out. All right, so what do we want to do? We also want to talk about bases. Right? Oh, so this is, by the way, I should write it, is a weak acid, right? Incomplete dissociation. And in many cases, very, very small amount, right? You're like talking 10 to the minus 5, 10 to the minus 7, 10 to the minus 10th, okay? And we'll get to the math of that. We also need to know our strong and weak bases. The exact same stuff occurs, right? A strong base completely dissociates in water to form OH minus. A weak base doesn't. And just like the strong acids, there's only a few strong bases that you do need to recognize, and so we will list those here. Strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, and I could do these in order here. Strontium hydroxide and barium hydroxide. Professor Clements, that's a funny way to write those. Why did you write those in that direction? Well, look, I've got lithium, sodium, potassium, calcium, strontium, barium. If you look at a periodic table in the alkali metals, what do you see? Lithium, sodium, potassium. Next to potassium is calcium, strontium, barium. Okay, so if you've ever played Tetris, you can remember your strong bases by just playing Tetris with the periodic table. It's not exactly the shape of the Tetris piece, I know, it's a little too long, but lithium, sodium, potassium across to calcium, strontium, barium, that little zigzag piece is your list of strong bases. Everything else that you run across that's a base, weak base. So we need to know, right? 0.1 molar lithium hydroxide gives me 0.1 molar hydroxide. 0.1 molar calcium hydroxide gives me 0.2 molar hydroxide, right? Because there's that 2 there. So it completely falls apart, right? OH, you get 2 OH minus for every calcium. So we need to know that, we need to recognize that so that when we have something other than that, we can be like, oh, now I need to do my ice tables, I need to do these other things that we're going to talk about. All right, that's our strong acids, strong bases. Know those, have them down. Whether or not you're in a class of mine that allows you to use notes on a test, just know those because it's so much easier just to recognize it and be done than it is to have to try to look things up. All right, so do you memorize them yet? I know, we just covered them. I'm so unreasonable. All right, which of the following is a strong acid? HClO3, HNO2, HI, HC2H3O2, HF. Go! All right, what did you come up with? Well, you're like, well, I just had to go look back at that list, and the friendliest acid on the planet, hi, is the one that is strong, okay? The rest of those are weak. Chloric acid, nitrous acid, acetic acid, and hydrofluoric acid are all weak acids. Everybody else is strong. So that is our foray into defining acids and bases, looking at their reactions, saying, hey, we're going to use equilibrium constants. They're exactly the same as the ones we did when we were just talking about equilibrium. We're just going to put a new letter on it. And then we talked about strong and weak and how we need to recognize those so we know, are we talking about a problem where everything dissociates? Are we talking about a problem where we have to do equilibrium work? Thanks for listening, and I look forward to doing a lot more numbers with you in this chapter. Yay!